Hello and welcome to Doc Clay's Chemistry Lessons. Today we're going to be looking at AQA A-level chemistry and we're going to be looking at the redox titrations in the transition metals topic. So just a reminder, if you've not already done so, do go and check out my website, Dr. Clay's A-level chemistry, where you're going to get lots of resources along with plenty of live webinars and assistance throughout the A-level course to improve your grades. And today we're looking at redox titrations, and by the end of this lesson we should be able to know how to perform and about redox titrations for Fe2+, C2O42-, which is ethane dioate, and manganate. Okay, so in the redox titration, we're pretty similar to the AS course where we've looked at acid-base titrations, but instead of using an indicator and an acid and a base, we're using a transition metal complex and we're observing the oxidation and reduction reactions. We'll look at those specifically in a moment. If you can't quite recall how to do a titration, then I'd encourage you to look at the Practical Skills 1 video from the AS course, because performing a titration is a required practical. The AQA only asks for it to be the acid-base one, but there's no reason why they couldn't ask about the same process here with a redox titration. So here we just got a quick setup of how you might expect to see this experiment done. Here we got the burette in which we got an oxidizing agent. So the oxidizing agent that we're looking in is the thing that will oxidize other things, in other words will be reduced itself, and we'll be looking at this in just a moment. The oxidizing agent which we'll be talking about is MnO4-. And then into the conical flask here we've got the other substance here, and that's going to be the thing that is oxidized, and we'll be seeing that this can be either Fe2+ in some form, iron 2+, or it can be ethane dioate, which is C2O42-. And just to show you what ethane dioate looks like, if you can't remember from your organic chemistry, it's 2 carbons based on a dicarboxylic acid here, but they've each lost their hydrogen ion. So there's our ethane dioate. Now the key about these reactions is that we're using manganate, MnO4-, and we're reacting it to form Mn2+. Now the manganate has got a distinct purple colour, while the manganese over here, or the Mn2+ here, is colourless. You can just balance this up here, so I'll just add in the state symbols to start with, and then we're going to add, remember, waters to balance the oxygen, so we add 4H2O liquid. We're going to add hydrogen ions here to balance up the hydrogens in the water, and then we need to add electrons to balance the charge. So here overall we've got +2, while on the left hand side we've got, if we add these up, we've got +7. So in order to balance this up we need to add 5 electrons. So this reaction, the MnO4- going to the Mn2+, is a reduction, and the key here is it changes colour. And this is going to keep changing colour while we have something that is willing to be oxidized in our conical flask. As soon as we've oxidized everything in our conical flask, what happens is we start to see a purple tinge form, and then we know we are at the end point of the reaction. We've got the same amount of MnO4- added as we do of either the iron 2+ or ethane dioate. What we're going to do now is we're just going to go and look at how we can balance the two equations for the manganate to make Mn2+ with the iron 2+ and the ethane dioate, and then we'll look at a couple of brief examples. Okay, so the first thing we're going to do here then is we're going to look at the reaction between MnO4- and Fe2+. So the first thing we're going to do is we're going to write out the two half equations here. So we just showed you how to work out the manganate one. I'm not including state symbols here, but we should do. You can either remember these or just remember how to work them out. I tend to remember how to work them out, but it doesn't really matter how you get there as long as you do. And then the reaction we compare here is with Fe2+ going to form iron 3+ in solution plus an electron. Now to balance these up and make a full redox equation, well, what we do is we multiply up to get a common number of electrons, then add the two reactions together to cancel the electrons. So our total redox equation, made up from the reduction and the oxidation, we get MnO4- plus 5 Fe2+, because we multiplied this one by 5, plus 8 H+. We've now cancelled the electrons, so we don't need to include these in the full equation. We make Mn2+ plus 5 Fe3+ plus 4 H2O. That becomes our balanced redox equation, and we can use that for our redox titration. We'll have a look at doing that now. So here we go, we've got our question, aqueous potassium manganate 7, well that's our MnO4- that we were talking about before, with a concentration of 8 times 10 to the minus 3 mole DM-3 was used to completely oxidize 25 cm³ of 0.06 mole acidified iron 2 sulfate. Well, we're acidified iron 2 to ensure that it's all fully reduced to make iron 2 from iron 3. And the question is to calculate the volume of potassium manganate 7 solution that was used in this reaction. Well, the first thing we do is we have to work out the balanced redox equation, which we've actually already done here. And we've already said this. And the second step then here is to work out something we know, in other words, to work out the moles of Fe2+. And the moles of Fe2+ is going to be equal to the volume times the concentration over 1000. So this really is sort of synoptic in the essence because it's using your AS knowledge but just in a different sense. And we end up with 0.06. I'm not going to add in the extra zeros here, although that does define really how many significant figures we should probably use at the end. The fact that we've got everything in 3 significant figures. And we end up with 1.5 times 10 to the minus 3 moles of the Fe2+. Now this is normally the difficult step in the sense that we've got the moles of Fe2+, and we're now interested in finding out the moles of MnO4-, and so the next step here really is to work out the moles, I should have said of Fe2+ here, moles of MnO4- is going to be equal to the moles of Fe2+ divided by 5, because there's a 1:5 ratio. And so if we put that into our calculator, we get 1.5 times 10 to the minus 3 divided by 5, giving us equal to 3 times 10 to the minus 4 moles of MnO4-. Finally, we just got to work out the concentration here, the volume here. So the volume of MnO4- is equal to the moles times 1000 over the concentration which we're given. So we are 3 times 10 to the minus 4 times by 1000 over our concentration here of 0.008, giving us a final value here of 37.5 centimeters cubed of potassium manganate. Our volume there in centimeters cubed because we've got a factor of 1000 throughout the question. The next one then we'll look at is going to be the MnO4- and C2O42-, which I said once again is ethane dioate. So once again we've got our manganate reduction reaction here, which you may well find that you just remember after a while, or you can work out in the exam. Remember here, we're purple on the left hand side and colourless on the right hand side. And we've got 4 waters. Now ethane dioate here, which is C2O42-, is a species which is going to be oxidized, and that gets oxidized to 2 carbon dioxides, and we also have here 2 electrons. So to write the full redox equation here, we're going to multiply the top one up by 2 and the second one up by 5 to give us our balanced redox equation. So if we write the full redox equation this time, remembering to cancel the electrons, we've got 2MnO4- plus this time 16H+, plus 5 ethane dioates. And we're going to go forward and make 2Mn2+, plus 8H2O, plus this time we've got 10 carbon dioxides. There we've got once again our full redox equation, which is made up from a reduction and an oxidation reaction. Okay, so we're going to use this to work out an answer to the following question, where we've got 27.5 cm³ of 0.02 mole potassium manganate reacted with 12.5 cm³ of acidified sodium ethane dioate solution, and asked to calculate the concentration of C2O42-. So first thing again is to write the balanced redox equation. Then we're going to find out the moles of something we know. So here we're doing moles of MnO4- because we've got lots of information about that. We've got volume and concentration. So once again we're volume times concentration over 1000. That's going to give us 0.02. Again, I've removed the 2 zeros, but we are there with 3 significant figures. Times by 27.5 over 1000, giving us a moles of 5.5 times 10 to the minus 4 moles of MnO4-. The next thing to do then is to work out the moles of ethane dioate from the moles of MnO4-. And again, we use this one in the AQA exam probably because it's a reasonably difficult sort of conversion that we do here, because we're looking at a 2:5 ratio. And so the moles of C2O42- is equal to the moles of MnO4- multiplied by, in this case, well, we're 2 to 5, so the is either going to be multiplied by 5 over 2 or multiplied by 2.5, whatever you prefer. So I could write 5 over 2, or you could write 2.5. Doesn't really matter how you come to that answer, but that's just what it is, because that's what we got from the stoichiometry of the reaction, giving us a total here of 1.375 times 10 to the minus 3 moles of ethane dioate. And the final step that we're being asked for is to work out the concentration here of the ethane dioate. And once again, we're just going to rearrange our volume concentration. So we volume times by moles times by 1000 over the volume to get our concentration. We put our values in here, 1.375 times 10 to the minus 3 times 1000. Well, that's going to give us 1.375 over the volume, which we've got in centimeters cubed here, and that gives us an answer of 0.110 mole dm minus 3. Okay, so that's the end of transition metal redox titrations. You should be able to know and perform redox titrations for Fe2+ and ethane dioate with MnO4-. Don't forget to check out my website for lots of more resources, lots of past exam paper questions, and also the webinars which are happening twice a week all the way through the exam period. I look forward to seeing you soon. Bye for now.